See later on by the time we get to chapter 13 of work. It's not a very hard chapter, but what makes it challenging is this chapter, almost everything in it is new. And that's what makes it challenging. So I'm going to tell you. So in this chapter, we're going to learn what are the actions, organic reactions. It's a new concept, right? We're going to learn what a mechanism is. It's a new concept. We're going to learn what a synthesis is. It's a new concept. That's what makes it challenging, because I have to explain those things from a new perspective, and of course, you know, think about gyration and other stuff. And what makes the reaction go, what makes it go this way, etc. So a lot of different variables that we learn in this chapter. When we get to chapter 8, even though the chapter itself has more challenging material, it's going to be easier. Why is that? We're learning more reactions. We already know what a reaction looks like. We're learning more mechanisms. We already know what a mechanism is. We're learning more synthesis. We've done that. Chapter 9, we're going to repeat the same thing, 10, 11, 12, and 13. So it's all going so for the rest of the semester, we're going to do everything based on this. So you're going to see it for the first time. It's going to be a little challenging, so just be patient. It's going to work out. Don't give up right away. But it is a little challenging at the beginning because it's all new. And what we're learning in this chapter is nucleophilic substitution and lineage. No fighting. What happened? So, alkyl halide. Alkyl halide. Think about an alkyl. A methyl is an alkyl. An ethyl is an alkyl. 6 carbon is a. When we say alkyl halide, that means an alkane with a halogen. What are the halogens? Fluorine, bromine, and so when we say alkyl halide, it's an alkane, right? Or an alkene, and by the way, I want to tell you now, we're really not concerned with the next two because these two cover an orgo too. So I'm not saying that I don't care about them. I do, but I'm not the one who's going to teach them. So I'm going to stick to the first, right? STP. So alkyl halide is an alkane with a fluorine, bromine, and we're going to put an X on fluorine plus fluorine. Alkyl halide that contains fluorine won't need to react. So guess what? We're going to omit. I don't know why they call it alkyl halide, because it's actually not halide. It's fluorine and some extent. Or if you look at all those exams, you're going to see a lot of fluorine, a lot of fluorine. But just keep in mind, fluorine does not. So alkyl halides are alkanes that have a halogen attached to them. And notice what they did is they wrote fluorine, bromine, and even though fluorine is a halogen, it's not really a reactive one, so it doesn't work for those reactions. So the two reactions that can happen, and this is kind of in a nutshell. If this, whatever it is, attacks this carbon, if your pair of electrons attack a carbon, it's called a nucleophilic attack, and that reaction is called the nucleophilic substitution. If the same molecule, they wrote it on that, it's the same thing. If it attacks a hydrogen here, if it attacks a hydrogen here, it's a proton. That means it's acting as a base. So if this thing acts as a nucleophile, it's a nucleophilic substitution. If the same thing acts as a base, it's a nucleation. And by the way, it's the same thing. And you're going to see later on that the same molecules can give you both. It's not like all these reactions give you a little bit of both. One of them is major, one of them is minor. One of them will be 90%, 110, and which one more depends on several factors. And what I want you to pay attention to are, what are the factors that determines whether we get elimination or substitution? Okay? So that's how we get spending time on. And the first thing I want to talk about is this molecule, which is this molecule, right? This molecule, let's say this is bromine, or chlorine, or hydrogen. This molecule is known as a substrate. I want to show you something about the substrate. This substrate, this chlorine, is on the carbon that's primary, because this carbon is attached only to one other. If I take the same molecule, same bromine, no magic trick, and I put it here, this bromine now is on a carbon that is secondary because it's attached to a carbon that has two other carbons. It will react differently just by changing one. As a matter of fact, if I exaggerate this a little bit and I make this into a same thing, still bromine, still carbon, but now this carbon is attached to the other carbons, the product with the same NUC nucleophile or base. Depending on what your substrate is, you get different products. As a matter of fact, with the first one, you get substitution. With the last one, you get elimination. And that's why I want you to pay attention to what I'm about to talk about, because changing the substrate changes the product. Same, whatever is single nucleophile, like OH minus, right? OH minus is a strong base, good nucleophile. What the product is depends on what this is and one other. So that's what we're going to be doing in the next step. Today and tomorrow. Don't worry, it's not just today. This is a two-class thing. So if the OH minus, right, OH minus, there are electrons, right? If the OH minus attacks here and the chlorine leaves, now OH minus is acting as a nucleophile, and you get this because it's a nucleophilic substitution. If the same molecule, OH minus, attacks this hydrogen and chlorine leaves, you end up with. So OH minus can be both an acid, a base, and a nucleophile. Now the reason I like OH minus is because you guys all know from January 2 that OH minus is a strong base. It's a strong base, it's also a strong nucleophile. Because it's a strong base and a strong nucleophile, it can act as either. And in this case, we get both. And guess which one is the major part? Actually, 7. This is the, that means it would rather act as a base, not a nucleophile. What kind of substrate is this? This is second. If this was the primary substrate, it would be 99% substitution, which is actually changes the whole. So that's why you have to pay attention, because a molecule like this, like OH minus, can act both as a nucleophile and as a base. And how it acts depends on a couple of other factors, including what the substrate is. So let's start with substitution. So a carbon with a bromine, halogen, that's what we said, okay, halogens, these we pick halogens, because you have to have a good leaving group. Halogens are really good leaving group, and the reason we use halogens is two. One's a good leaving group, but they're not the only one. There are other good leaving groups, but halogen molecules are also really cheap. So when if you want to make a drug, right? First you want to save some money, right? And you want a good leaving group, and halogens work. It doesn't have to be a halogen, there are other leaving groups. So halogen, bromine can be a nucleophile. So this is, let's say this is chlorine. This carbon is next to the chlorine. Carbon is less electronegative than, therefore carbon has a slight positive charge. So a pair of electrons, a nucleophile, will attack that carbon. Why is that? Because this carbon has a positive charge. Once it attacks, this must, because we can't have 5 bonds. And so that's what a nucleophilic substitution is. A nucleophile replaces X. And just for, X could be anything. Again, I want to tell you this, but for our purposes, for this chapter, it's going to be a chlorine, bromine, iodine. So, but it could be anything else. So nucleophile attacks the carbon, and the halogen will be replaced. That's why it's called the nucleophilic substitution. You are substituting a nucleophile for a halogen. So if you start with bromine and you add OH, it's going to be OH and bromine is. If you start with chlorine and you add NH2 minus, it's going to be NH and 2 and chlorine is. So the halogen is the leading group that must lead in an elimination or substitution. So what are really good leading groups? Look at on top. Iodine, bromine, chlorine. These are really good. And that's why this chapter is using halogen molecules. By the way, this is a very good leading group. This is mesylate, don't worry. We'll cover those in chapter 11. That molecule is stabilized by resonance. Anything that's neutral is good. Anything below this line does not lead. Please write that down somewhere. Anything below this line does not lead. Fluorine. You cannot have a substitution reaction with fluorine. OH minus. Conjugate bases and NH. Now, here's an example. Let's say we had a really good nucleophile. Could we have a nucleophilic substitution here? Can this attack and this lead? And the answer is no. Why not? OH is not a good. By the way, what you memorize is just the top. There's 5 of them. It's F minus OH and all the alcohols, but just if you memorize one alcohol, you remember the rest, right? So OH minus does not, if the leading group is not a good leading group, can you have a reaction? No, it doesn't want to lead, it's going to be sticking around, so how could you have a substitution or elimination? In order to have a substitution or elimination, you have to have something that can be replaced who's happy to. So really good leading groups are on top. Iodine, bromine, Cl minus. These are stabilized by resonance as well as anything that's neutral. F minus and OH minus are horrible leading, and they never. So alkyl halides are molecules that contain chlorine, bromine, and iodine. If you want to name them, guess what?
Thank you.
Go back to chapter 4. How do we name a molecule? Find the longest continuous chain with the most. Name. Number 12 with the lowest number possible, and then arrange alphabetical order. It's the same thing except if you have a methyl, if you have instead of a methyl a bromine, guess what? Fluoride, bromine. If you have instead of a methyl you have a fluorine, you write fluoro, so it's chloro, bromide, orgo, and you arrange them also in alphabetical order, right? So bromine, if you have a bromo will come way at the beginning because it's the only thing lower than bromine is what? Even butane is lower. It's high, right? So bromo will be like usually first. So just keep in mind it's alphabetical order and the naming is the same. So 1, 2, 3, this is a 3, so it's propane. Chlorine is on 2, so this is 2 chloro. Propane. 1, 2, 3, 4, 5, so that's a pentane. There's a methyl and a bromo. Both are on 2, so it's 2 bromo, 2 methyl, pentane, and you see where I'm going. So, if the carbon that has a halogen attached to it, this is the carbon that has the halogen attached to it. If that carbon is attached to one other carbon, it's called the primary halide.
This carbon has only one. If the carbon attached to the halogen has two carbons, the carbon attached to the halogen has two carbons attached to it, that's a secondary alkyl. If the carbon attached to the halogen has, you see I'm going with this, right? Three carbons attached to it. You see that, right? It has no hydrogens. This carbon, which has the bromine, chlorine, whatever it is, iodine, has a carbon attached to three other carbons, that's a tertiary alkyl. Primary, secondary, and tertiary alkyl determine what the product is. Like this can't have substitution with strong nucleophile, whereas this can't have elimination. And that's why, don't worry, we're going to cover those, but so if you know what the alkyl halide is, you can tell what the product is going. These are some more alkyl halides. And DDT, by the way, you guys are too young to know what DDT. Anybody knows what DDT is? What? Oh yeah, it's an insecticide, yeah, pesticide that kills everything, including animals, fish, sadly not humans. Birds. So alkyl halides are molecules that contains a halogen. So substitution. Let's go to substitution. And I talked about this yesterday. I know we laughed about it. This is actually going to be done. If I have a nucleophile, this is my nucleophile, there's my alkyl halide. This is the halogen that is going to be replaced. Right? Substitution means replace the halogen by the. This can happen in two ways. Number one, the halogen can leave at the same time this takes its. Because we bind this, right? Happens at the same. Or the other way it can happen is we have an alkyl halide. Halogen leaves at some point later the nucleophile takes its. It's still the same product. We still ended up with a halogen leaving and a nucleophile replacing it. One happens in one single concerted step, and the other happens in more than one step. It happens. And so we're going to start with the concerted step. When it happens all at the same time. The nucleophile attacks the carbon, and the halogen leaves all at the same. So the concerted reaction means the attacking group and the leaving group must happen. You can't break one or form one. So basically, they come close together. I just want to show that. They get close together, but it's an sp3 here. As the orbital overlap changes to this, the orbital overlap, basically just bond forms here and bond separates from here at the same time. So this is a concerted mechanism. The other one, which we're not going to cover today, this is probably going to be tomorrow, is same kind of idea, right? It's still a nucleophilic substitution. The halogen leaves, right? You end up with the carbon. Then the nucleophile will, at some point later on, attack. And by the way, when I say at some point later on, I'm talking like tens of billions of a second. When I say some point, it's not like 3 days later. It just happens. But it's separate. It's not at the same time. And this will be not today. So we're going to start with the concerted substitution, the one that happens in one step. So the reaction is called SM2. S stands for, it's a substitution reaction. So S stands for
Substitution.
We need a strong nucleophile. And therefore, N stands for nucleophile. 2 is the order of the reaction. What is any order of reaction? That means the reaction is second order. I don't remember from yesterday. A first order reaction depends only on one model. A second order reaction depends on present at the same time in order for the reaction to proceed, right? So this is, so SN2 reaction is a substitution nucleophilic bimolecular, and for second order. And what happens is the nucleophile attacks the carbon, because that's what nucleophile does, and the leaving group leaves all happens at the same. And notice now, all what happened is we replace the halogen X leaving group with a nucleophile. So far, so good. This is an important slide. So it turns out SN2 reaction, the way it happens is what I'm going to show you. So we have the halogen, we have the nucleophile attack. Now let's think about this for a second. If I form a bond here, and disappear, guess what? The bonds are going to be pointed this way, right? That's not possible because this is sp3. You can't have it. So what happens is, I'm going to tell you, when this arrives here and the bond is formed, this flips to the other side. How does it flip to the other side? It's basically, you have the electrons this way, right? When the nucleophile arrives, they just flip. I'm going to give you an example of that. You ever had an umbrella and you walk in and it's raining and it's really windy? Right? What happens if it gets really windy? Right? The umbrella just, that's exactly what happens. So what happened is the two atoms here, they will flip to the other side. So this is known as inversion of configuration. It's just like an umbrella. Once the nucleophile arrives, you want a really burst of wind. You don't like that, but the umbrella will flip. And so what happens is when I want to show you. So this is the nucleophile, right? The nucleophile is arriving from here, right? Nucleophile is arriving. Notice in the product where the natural hydrogen and natural are going. Here they're pointed this way, right? What happened in the product? It's the umbrella. They went poof, and now they pointed the other way. And why is that important? That's important because if you start with a configuration of S, and you flip everything, it will be the opposite. You will end up with R. And if you start with R, you will end up with S. So this is really important for SN2 reactions. SN2 reactions are always accompanied by inversion of configuration. You start with R, you end with S. You start with S, you end with. So if you want to make an S molecule, it would be stupid if you start with an S molecule. Because if you start with an S molecule, you end up with. So you have to plan ahead. So these reactions are accompanied by inversion configuration because when the nucleophile attacks, it attacks from here, and the other things flip. And the other thing, there's a couple of things tricky about this. I'm going to tell you. You know what? I'll draw it. You guys know I can't draw, so please bear with me. So say we have a carbon. And there is my, so pay attention. The nucleophile can only attack if it's lined up with the carbon and the bromine. That means the carbon, bromine, and nucleophile must be all in a straight line. That means the bond angle is what? 1. The nucleophile cannot attack from this angle. It can't attack from this angle. It can't attack from here. It can only attack if it's lined up. So I'm going to show you. So this is my bromine. So in order for the reaction to proceed, if the nucleophile attacks from here, guess what? What about here? What about here? All these reactions don't need a problem. The only way this reaction will proceed is if the nucleophile is coming exactly from the back, right? It's called the backside attack. It's attack and it has to be lined up. Right? Not like at an angle. They have to all be in a straight line for the reaction That's really important to remember for SM2 reaction. So nucleophilic attack can only happen if the nucleophile, when it attacks, it's exactly lined up, with the carbon, and it has to be in a straight line. Any other angle, no reaction. So if the chlorine attacks from here, the nucleophile, the action will not take. And so these two things are important. One, if we have a stereochemistry RS, we're always going to end up with the opposite. Right? That's important. The other thing is when we attack, it attacks from the backside. So it's a backside attack. By the way, they draw this to make you understand. I don't know, this seems more confusing. What I care about is you knowing, right? I want to tell you. You knowing the only way the action can proceed is if the nucleophile attacks from the back. Anywhere else, no reaction, right? That's to do with the overall distribution. So the nucleophile attacks from the back, lined up with the carbon and the leaving group, and leaving group leaves, and we end up with inversion of configuration. And of course, in the transition state, just think about, there's a picture about it, but think about what's happening is, as this molecule is forming a bond, the HBr is breaking the bond at the same time. Right? It's not two separate events. So, important things to remember. In order for SL1 reaction, the first one to remember is the substrate. What is the substrate? It's the molecule itself. This is a primary substrate. Why is this a primary substrate? Because it's attached to only one. Now, I'm going to ask for a volunteer. How about you in front? Michael?
All right. 3 fingers. I want you to touch this card. Back side of it. Did you have a problem? No? It's straight up, right? With nothing in the way? Right. So, primary substrate is perfect because there's nothing in the. Right? Let's do a secondary substrate. I want to touch that card. What is it less easy? You have to be a little careful because this is in the way, right? So secondary substrate is less reactive because if you want to come from the backside exactly, guess what? This is going to be in the. So if no matter what I do, yes, at some point if this moves I can, but not always, right? What if I have a tertiary substrate? I don't want it. Actually. Did you touch first or did I? Okay, so there's no way you can reach, you cannot pass here without, write this down. Tertiary substrates cannot undergo SN2. So if you have a tertiary substrate, guess what? Can you have a SN2 reaction? No. Actually, primary is perfect. Primary is perfect for SN2. Secondary is I'm going to say, what does that mean? They can happen. He actually was able to finish. Tertiary substrate cannot undergo SN2. Never. Please write that down because exam day, you guys make up shit. Tertiary substrate, SN2 reaction. Perfect. So please write that down. Why is that? Because in order for the reaction to proceed, right, I gotta reach here with all this stuff in the. This is called steric hindrance. Yesterday we mentioned the word steric, but I don't want to talk about it. What steric hindrance is when you have a molecule and the action can't proceed, it's actually called shit in the way. I'm trying to reach. I can reach because when I took organic chemistry, I had a British professor. I took organic chemistry in this room, by the way. And he didn't like writing anything down. And he had no slides. And during he fought, and he would sit here and
talk to local ones. Never stood up. Like, he would just sit and talk. And good luck. Like, imagine learning organic chemistry without seeing anything and he would explain things. But he had a good example. So he said, let me tell you how he explained his treatment. He said, let me explain his treatment. He goes, when I was a young lad, back in Phoenix, I had an uncle and an aunt. Uncle John and Aunt Edith. And they were two very bad people. And I often wonder, how do they do it? I swear this time. It's all inappropriate, but in any case, so Stephen says, when you actually got, you can't have a reaction because shit gets in the, and so tertiary substrate cannot undergo SN2 reactions because of steering. If I move these, right? If I move these, I don't have a problem. I can just have a reaction, right? SN. If I make it into a primary substrate, I'm good, right? Once I get to secondary, it becomes a little more challenging. It still can happen, but not as easy. Once you get to a tertiary substrate, you cannot have SN2 reaction with a tertiary substrate because of steering. So that's really important to remember. Tertiary substrate, no SN, no substitution reaction. Why is that important? Guess what? If tertiary substrate cannot undergo SN2, it has to undergo something else. Remember, this chapter is substitution and elimination. So if you have a strong nucleophile, strong base, and it cannot go SN2, guess what? The only choice we have is elimination. If it's not substitution, it's going to be elimination, and just keep that in mind. So, and of course here it shows you why. Primary substrate is easy for the reaction to proceed because you have the backside of tag, whereas as it gets bulky, like you can see that the tertiary substrate is not. Now, this is still a primary substrate, but think about it, even if you have a primary substrate, right? If I have a primary substrate and I put a lot of things here in the way, like build a tree, it's still going to be hard to reach, and that makes it more. So just keep in mind that it's all about steric hindrance, but tertiary reactions, the substrate, definitely don't work for SN2. No. And the reason for that is reaction goes through a transition state, the nucleophile attacks from the back, and as the nucleophile carbon bond is formed, the bromine carbon bond is being broken. All happens at the same time. This is a one-step reaction. That's why it's only one. What if it was a two-step reaction?